My name is Juan Pablo Reda Gallardo. I am a student of the Laboratory of Characterization of Nanomaterials, and this is my extra activity. Upon the article that talks about characterization methods for nanoparticle, I picked four, which are SPMR, superparamagnetic relaxometry, X-ray magnetic circular dichroism or XMCD. I pick Mossbauer spectroscopy and electron diffraction. And I'm going to talk about how these techniques work and a specific example of how these techniques are used to characterize nanoparticles. Okay, first talking about superparamagnetic relaxation or SPMR is a technique that measures the relaxation rate of superparamagnetic nanoparticles when an external magnetic field is removed. The relaxation signal, typically measured by detection coils, is a function of their rotability in these nanoparticles. It provides information such as hydrodynamic size of nanoparticles in a liquid medium, and it can differentiate single nanoparticles or free nanoparticles from agglomerated nanoparticles, making it valuable for quantifying the state of dispersion to see if we have like a bunch of nanoparticles together or if we have free nanoparticles roaming around in the solution. And for the example that I chose, it's a it's a technique that it's used with highly sensitive squid sensors that are specifically designed for this, operating at cryogenic temperatures that can detect weak magnetic signal for nanoparticles that can be used for 3D mapping the human body and detecting where tumor cells are. And with that, we can just have like sub-millimeter precision and be more specific targeting a tumor than with just general chemotherapy. The second technique is X-ray magnetic circular dichroism or XMD. Okay, XMD works is that it actually uses polarized X-ray from a synchrotron to investigate the magnetic properties of materials. The technique measures difference absorption of the X-rays and the material. The absorption is directly proportional to the magnetic moments or specific elements of the atoms. The information that it provides, well, it's very specific. It can determine the magnetic moments of each type of atom in a complex nanomaterial. It can also differentiate between spin and orbital magnetism and a lot of magnetic properties. This technique is mostly used with metallic nanoparticles or nanomaterials that have metals in it, for example, like the muff we made with zinc. For the reference example that I chose, it's that it can be used to analyze magnetic properties on iron magnetite, not magnetite, magnetite. Going beyond as well simple analysis, that would just be like looking at them and doing some simple proofs. And researchers did it by using XMCD at these L2-3 edges of iron to differentiate between the tetrahedral shape and the octahedral sites with the spin structure of the magnemite. Well, this technique is very sensitive to the sides of these atoms, and they gave like specific information about the momentum and how this can be used in future applications. Well, the third is Mossbauer spectroscopy, and Mossbauer spectroscopy works like similar to nuclear magnetic resonance, but with slightly differences. Well, it works specifically by at the absorption and the emission of gamma rays by certain atomic nuclei. The resonance is extremely sensitive to the chemical and magnetic environment of the nucleus, and the information that it provides, well, it's very specific to certain atoms because it's like our NMR that gives us specific information about hydrogen, about I think that silica, carbon, obviously, and all the other NMR that we can use in the lab. But this Mossbauer gives us specific information about, for example, iron, 57 or 10, 119, which are like isotopes of the normal atom. It provides also information about the oxidation state. For example, like this isomer shift between the normal particle and these and this other new particle with of this is isomer. And also it could give us like a symmetry because we could give like an idea of how the molecule is shaped by the gamma rays that it emits. And for the reference example that I chose, I picked well, it can be used to discriminate between iron in core and iron in the outer shell of magnetite nanoparticles that have like an interest to nanomedicine. For example, it says that sorry, that magnetite has an inverse spinel structure with iron in both Fe2 plus and Fe3 plus in oxidation states, and that most Bauer can differentiate between the core and the surface magnetite nanoparticles due to the behavior that they have on these locations. For example, in the particle core, ions tend like behaves like those in bulk magnetite, showing like well-defined most Bauer parameters that we can see it in the spectra, like really well defined compared to what those in the outer shell that are like that have a greater disorder and can exhibit like supermagnetic relaxation. And last technique that I chose is electron diffraction, and electron diffraction is typically performed in a TEM, in a translation electron microscope. A beam of high energy electrons is directed to a thin crystalline sample, and then the electrons are scattered across a detector that we can read with specialized software. And the information that it provides, well, it's crucially for crystalline structure of whatever that can have a crystalline structure. For the reference example that I chose, well, I chose that it could be super uh, super very important for obtaining the structure of 3D nanocrystals, which are less crystals of less than 500 nanometers of proteins, because an electron beam will its high energy and it can give us this pattern pretty well of the nanocrystals, but unfortunately it's a technique that has not been studied a lot, and that also has like some issues with the scalability and in order to being like a wide use technique. So this could be like a pretty huge, but unfortunately it needs more research. And last, for the reflections that it's asked, for example, it says that are all the techniques suitable for different nanomaterials? And well, the obvious answer is no. We can use, for example, a technique for magnetic nanomaterials that could be like SPMR on non-magnetic nanomaterials, because we wouldn't get any data of it. We would just be wasting time and sample. Other question is, what is important of using different techniques to characterize a single nanomaterial? Well, I think it's essential to use like complementary techniques to obtain the most data that we can out of the nanomaterial. For example, with the synthesis of silver nanoparticles that we're doing, and by the characterization with UV and with DLS, we can get information about like set potential and how the nanoparticle works, if it's agglomerated, if it's like free roaming, and that could give us like a lot of valuable data on the particle or the material, and that can be used, for example, in nanomedicine or in materials or in whatever field we want to. The third says that if a material is characterized only by structural techniques, what type of information would be missing if you missed characterization by spectroscopy techniques? Well, if a material is characterized only by structural techniques, we wouldn't get like information like uh, we would get information like the morphology, size, shape, basic information. Well, not so basic information, but information about just how the material looks, but know about how it behaves under certain conditions. And I think that's pretty important to know how it looks and how it behaves under certain conditions in order to know if the nanomaterial nanoparticle has an application to any other field that we want to do. The last says, if two techniques that are completely give contradictory results, what would you do? And I think this is pretty. It gives a lot of debate because some people might say, like, well, if you gave contrary results, well, obviously you did something wrong, but what we need to do is like check if all we did is right, because some techniques are complementary and can give contradictory results if we did something wrong, if we set wrong the parameters, if this nanomaterial was wrong, if we had something extra, etc., etc., etc. So we what we could do is try to find the reason of the contradictory, and if after we did the experiment at least a certain amount of times to see if the variable is really in the experiment in the nanomaterial, or it's just like the design, the method of the experiment that we're doing. I think that would be like a pretty huge huge result and a huge answer of what we could do with that nanomaterial.